Let's see, Cryptography Lecture 8, and the question is, on the review sheet, to look at problem 15 on the RSA digital signature protocol. So Bob wants to be able to send a message, and the recipient has to know that he is the sender and not someone else who's trying to deceive people. So Bob chooses secret primes p equal 5 and q equal to 11. And Bob chooses the verification exponent e equal to 3. And what Bob publishes tells everybody in the world the number n, which is p times q, which is 55, and e equals 3. So no one knows what p and q are, but they know the product is 55, and they know there's this another number 3 that's involved. So the first thing you need to do is to compute d such that dE is congruent to 1 mod p minus 1 q minus 1, which means dE is 3d congruent to 1, p minus 1 is 4, q minus 1 is 10, so 3d congruent to 1 mod 40. And you can do that any way you like. I mean, I would just note that 3 times 13 is 39, which is minus 1 mod 40. So 3 times minus 13 will be minus 39, which is 1 mod 40. So D can be any number congruent to minus 13. And if we like positive numbers, we would pick 27 mod 40. So D equal 27 works. And of course, you can check. 3 times 27 is 81, which is congruent to 1 mod 40. Okay, so that's D. And now you have a document D, which is the number 343. And so Bob wants to send this document, and people have to know it's he that's sending it. So he signs the document. His signature is S congruent to D to the D mod n, which means S is going to be 343 raised to the power 27 mod 55. So you have to calculate this, and let's see. Of course, 55 is pretty small compared to 343. So I can simplify this right away by saying, let's see, what is 55? 110, 330. This is, I think 343 is congruent to 13 mod 55. Because 330 is 6 times 55. So this is the same as 13 to the 27th power mod 55. And offhand, I don't know any easy way to compute that, but if you really want to know what it is, if you take, I'm just looking, I'm using Maple, on my computer, I take 13 to the power of 27 and I divide it by 55, the remainder is 7. So the signed document that Bob sends is just the number 7. And whoever gets this document wants to verify that this is correct. So computes s to the power e mod n, and which is 7. What is e? 3. 7 to the power 3 mod 55. Let's see. 7 cubed is 343. What is this mod 55? It's 23. Oops, that's not good. Is that right? No. 7 cubed is 343, which is congruent to 13 mod 55. And that's the right answer. So
Professor.
oh, just 1 second. Yeah, I'm sorry. Go ahead.
Thank you. Can you
But
please
can you
go?
speak a little louder? It's hard for me to
Sure.
hear you right now.
Can you please go over number 1?
All right, just 1 second. I'll certainly go over number 1 in a moment, but I want to just talk about this digital signature for 1 more second. So I just want to make sure I explain one thing to make this clear. So Bob wants to send a document to someone, and he wants that person to know it's from him. So the document is D. So he sends D to the recipient. So, and what he sent, I wrote 343, which was silly. I should have just made this 313 because we're only considering things modulo 55. So let's say the document is the number 13. He sends that, but he needs to sign it in some way. The way he signs it is to take D to this power little d. His signature number is S, and he sends S. And then the recipient takes S to the power E. And if that person gets back 13, she knows that this is an authenticated document. So 13 is the documents that's sent. Bob has to prove he's the guy who sent it. So this procedure, he signs it in this way, and the verification, this is his signature, is that S to the E gives you back 13. And the only way you know you got 13 is because you know whoever sent the document knew the number D, and no one knows D. You can't know D without factoring N to get P and Q, or P minus 1, Q minus 1. That's the idea. Okay. You asked about number 1. Number 1 is just the Caesar code. So this is from Roman times. You have, you can do it using a circle, but I'll just write it as A, B, C, D, E, and so forth. And if you're going to shift numbers by letters by 3, when you encode a letter, like suppose you want to, someone is named Deborah or Deb for short. So how does Deb encrypt her name? So if you're shifting every letter by 3, A becomes D, B becomes E, C becomes F, D becomes G, and so forth. So D is G, E, if you go 3 letters over, is H, B, if you go 3 letters over, is E. So when you encrypt Deb with a Caesar cipher shifting letters by 3, what you transmit is GHE. And whoever gets that, this is a symmetric code. You need the same secret knowledge to encode and decode. The secret knowledge is how large the shift is, in this case, 3. So whoever gets that says, okay, this is encrypted using the Caesar code shifting by 3. So to decipher this, to decrypt this, I go back by 3. So G becomes D, H becomes E, E becomes B. So this is the encryption, and this is the decryption. And this is presented at the very beginning of the first chapter as a kind of historical background about some codes that were used in ancient times.
Thank you, Professor.
Okay.
Professor, are we gonna, what's it? Is that it for now, or can we ask any
You have
more
another
questions?
question? Sure.
Just one more for now until I keep on going through the document. I had one more question, which was, which question was it again? Looking. Number 11 with the RSA public key crypto, the deciphering.
Mm-hmm.
See.
So in problem 11, Bob seems to like 5 and 11. So he chooses the prime P equal 5, Q equal 11. So the product N is 55, and his encryption secret key is E equals 3. And again, the numbers he publishes are 55 and 3. So he gets the ciphertext from Alice. So the ciphertext is the number 24. And how does he decipher it? How does he decrypt it? So you have to find a number D such that D times E is congruent to 1 mod P minus 1 times Q minus 1, or 3D congruent to 1 mod 40, which we did a few minutes ago. You can take D equal to 27. So if M was the plain text that Alice had, how did she encrypt it? Her encryption, C, was you take M and you raise it to the power 3 mod 55. And that is 24. And if you take the encrypted number Z, C, and you raise it to the D, this should be an E. This is M to the ED. M to the ED, or DE, is 1 mod P minus 1 Q minus 1. So this is congruent to M mod 55. So you decrypt the encrypted message C by raising it to the Dth power. So C is 24, D is 27, you have to compute 24 to the power 27 mod 55. And if I can't do that by hand, it's not in any obvious way right now, but if I use my computer, if I divide,
Excuse me, Professor, how did you get 24 again?
that was given.
It was
That's
given,
part of the
oh,
problem. Bob
okay.
receives the ciphertext C equal 24.
Okay, okay. Sorry, Professor.
So that's what comes through, that's what's transmitted to Bob. That's the encrypted text. And he has to recover the plain text. So he has to raise C to the power D, which is C to the power 24 to the power 27. So if you take 24 to the 27th power, and you look at what it's congruent to, mod 55, I get 29. So that's the answer.
Professor, can
Yes.
I ask, can I please ask one more question, please?
Yes.
Can you please do number 10, the one just above this problem?
Okay. So that's the encryption. That's the encryption part of RSA. So again, in problem 10, P is 5, Q is 11, N is 55, and E is 3. And Alice has the plain text M equal to 17. The ciphertext will be 17 to the power, it's M to the E, which is 17 cubed mod 55. So you just have to compute whatever 17 cubed is, mod 55. That's easy to do. You can do it by hand, or you can do it on a calculator. And when I just did it, I got C is equal to 18. That's all it is. It's just a congruence.
Thank you.
And Professor, what's it, are the questions gonna be like, what's it, like this in terms of like, because I remember the homework, like I said, like, it was like, we had like numbers dealing with it like 600,000, so like that, it's gonna be like,
No,
are they,
these will be very small numbers,
okay,
just to make sure, just to see if you understand the methods that are involved.
okay,
Because on a 2-hour test, there's not enough time to ask complicated numerical questions. And there's
okay.
no reason to. Okay, so let me start to do what we need to be doing for to learn some more cryptography. Next week, it's just a 3-day week because Wednesday is Juneteenth. There's no school. So next week we just meet Monday, Tuesday, and Thursday. And the following week we just meet Monday, Tuesday, Wednesday, and then there is the final exam. So our next topic is going to be more number theory. It's what is called elliptic curve cryptography. And an elliptic curve, let's see, I mean, what is an ellipse? There's not really a connection, but an ellipse, you might have an equation like x squared over 25 plus y squared over 9 equals 1. And if you graph that in the plane, you get this ellipse that looks like this. And that's the graph of this curve. An elliptic curve will generally have the form actually, if I wanted to write this in terms of y, it's an interesting exercise. So y squared over 4 is minus x squared over 25 plus 1. So this is y squared is minus 4 over 25 x squared plus 4. So y squared is equal to some quadratic equation in x. In an elliptic curve, you have an equation where y squared is a cubic in x, say x cubed plus 2x plus 3. And an equation with which is y squared on one side and a cubic on the other, the graph of this is something that's called an elliptic curve. And it will often have a shape that looks like this. I mean, there might be like a round part and then some infinite part. And somehow there's a connection, very clever connection, between elliptic curves, that means the points that satisfy this equation, and a way from that to construct a secret code method, a cryptographic scheme. And that's our next main topic. But to do that, we have to know a little bit more algebra. And in particular, a little bit about groups. So there's a nice section beginning in chapter 2. I believe it's on page 74. Find it. About groups. So our next topic that we need to understand is group theory. So some people in this course have had algebra and some people have not, and I'm going to assume no one has. So so what is a group? So a group is a set, we'll call it G for group, where you have some binary operation we can call it addition, we can call it multiplication, we can call it anything we like. Some binary operation, let me just use sort of a symbol star for the binary operation. That means that for all elements A and G and B and G, there is defined A star B that's in G. So for example, if we take G to be the integers and star to be addition, then 5 star 7 is 12. If we take G to be the rational numbers that are different from 0, so I'll write a G star there. 5 star 7, and then the operation is going to be multiplication. So 5 star 7 would be 35. So, and usually we use either addition or multiplication as the word for whatever is the binary operation, and it doesn't really matter what it is. So a group is a set where there's some way to combine two elements to get a third element. We can say we're multiplying them, we can say we're adding them, doesn't really matter what we call it, but there's some binary operation. And the ones you're most familiar with are addition of integers, real numbers, complex numbers, congruence classes, and so forth, or multiplications of them. So for all A and G, A and G and B and G, there's an element A star, A times B and G. I generally use, and most people use, multiplication as the generic operation. So with the following properties. The first is there's an identity element. There exists an element, I'll call it E, in the group, such that A times E and E times A are always equal to A. So for example, if you look at the integers under addition, the identity is just the number 0. If you look at the non-zero rational numbers under multiplication, the identity is the number 1. But whenever you have a group, there has to be an identity element, which is generically notated by E. Second, every element has to have an inverse. That means for all A in the group, there is another number. We'll write it as A to the minus 1 in the group, such that when you multiply A times A inverse, or in the opposite order, A inverse times A, you get the identity. And the third property which has to be satisfied is that the binary operation, multiplication, is associative. So you multiply A and B and multiply that by C, that's the same as multiplying A with B times C. So this is the definition of a group. Another very important example, if you take G to be the set of all 2 by 2 matrices, A, B, C, D, where A, B, C, and D, they can be real numbers or integers, it doesn't matter. But the determinant, or the number AD minus BC, is equal to 1. With the ordinary matrix multiplication, this set of 2 by 2 matrices is a group. And this is a very nice example. Now, some groups have an additional property, which is that they are commutative, which is also called abelian. And in this case, the order you multiply doesn't matter. A times B is always the same as B times A. So addition of integers is abelian. 5 plus 7 is 7 plus 5. Multiplication of rational numbers is abelian. 5 times 7 equals 7 times 5. But multiplication of matrices is non-abelian. It's not abelian. So you can have matrices A and B with AB and BA. They're both 2 by 2 matrices, but they're different. So there exist such things. So every group has to have an identity element. The multiplication has to be associative, and every element has an inverse. A group may or may not be commutative. And a finite group is just a group with a finite number of elements. What's called the order of the group G is just the number of elements in G, which we write often in G with absolute value signs around, and they're just this number sign times G. But this just means the order of the group. The number of elements, and finite group is a group with finitely many elements. If you take the integers mod m, this is an additive abelian group. So for example, if you take Z mod 12Z, 7 plus 9 is 6. No, it's 4. Right? And yes. Because everything is addition modulo 12. 7 plus 9 is congruent to 4 mod 12. If you take a prime number P, the finite field with P elements is just the congruence classes mod P. And if you take the non-zero classes, which is usually denoted by this is a set of numbers 1, 2, 3, up to P minus 1. And the fact that if A and P are relatively prime, then there exists a B such that AB is congruent to 1 mod P implies that FP star is a multiplicative group. The identity is just the congruence class of 1. Multiplication is associative. This says A has an inverse. So for example, if A is 3 and P is 7, we have 3 times 5 is 15 is congruent to 1 mod 7. So the inverse of 3 is equal to 5 in Z mod 7Z star. And multiplication is abelian this community. An example of a non-abelian group, one is the group of all 2 by 2 matrices A, B, C, D, where A, B, C, and D are real numbers, and AD minus BC is 1. If you just take all 2 by 2 matrices where AD minus BC is simply not equal to 0, this is a multiplicative group, which is a non-abelian. And you can see it's non-abelian by just taking almost a random example. If I take A to B, let's say 1, 0, 0, 2, and B equal to, I don't know, 0, 3, 4, 0. Let's see what happens when I multiply AB. 1, 0, 0, 2, 0, 3, 4, 0. If I multiply these, I get 0, 3, 8, 0. If I multiply B times A, I get 0, 3, 4, 0 times 1, 0, 0, 2. That's equal to 0, 4, 6, 0. 0, 4, 6, 0. And these are different. This is 3 and 8. This is 6 and 4. So in this very simple example of multiplying 2 2 by 2 matrices, the order you multiply in matters. A times B is different from B times A. Now, suppose that G is a group and that A be an element of G. Then we say that A has order D if D is the smallest positive integer such that a to the d, which means a times a times a, d times, is the identity. And again, we write a to the d if the operation is, we think of it as multiplication, the operation were addition, it would be d times a, which is a plus a plus a, d times equals 0, let's say, 0 with that happen. If no such d exists, then we say that a has infinite order. So for example, if we let G be the group Z mod 12Z under addition, if we take, let's say, A equal to 4, then 3 times 4 is 12, is 0 mod 12. So 4 has order 3 in Z mod 12Z. If we take G equal to 11, and we look at Z mod 11Z, and we take A equal to 4, then if you start looking at the multiples of 4, the smallest multiple of 4 that is divisible by 11 is 11. 11 times 4 is 44. It's congruent to 0 mod 12. So 4 has order 11 in Z mod 11Z. Suppose we take G to be the integers, and we take A equal 4. So if you start adding 4 to itself, 4, 8, 12, 16, 20, 24, and so forth, do you ever get 0? No. So A does not have finite order 4. So 4 has, we say, infinite order in the additive abelian group Z. Now, what is a fundamental fact about finite groups is that every element has finite order, and its order divides the order of the group. So this in the text in chapter 2 is proposition 212. Let's say G is a finite group. Every element of G has finite order. If A in G has order D, and the cardinality, and A to the K is the identity, then D divides K. So, and what does it mean to say A has order D? This means that A to the D is the identity, and D is the smallest integer with this property. So why is it the case that every element of G has finite order? So proof. Consider the sequence of powers of A. a squared, a cubed, a to the fourth, a to the fifth, and so forth. Now, if G is a finite group, then these powers cannot all be distinct, because we're generating an infinite sequence, but the group does not have infinitely many different elements. So at some point, there has to be a collision, a repetition. So there must exist positive integers I less than j with a to the I equal a to the j. Let's say I greater than j, to follow the notation of Texas. So we have a to the I equal a to the j. A has an inverse, so multiply by both sides by a inverse to the j. So a to the I, a inverse to the j, is a to the j, a inverse to the j, which is a to the j, a to the minus j, which is a to the 0. That's the identity. And this is a to the I minus j. So we have a positive integer, I minus j, is some positive integer because I was bigger than j. So a to this power is e. So there's some positive integer such that a to that positive integer is the identity. And this, so there's a smallest such positive integer, and that's the order. Now, suppose A has order D and K is an integer such that A to the K is A to the K is the identity. If you divide K by D, what do you get? K is D, oops, D times some quotient Q plus the remainder, where the remainder is, you're dividing by D, so the remainder is a non-negative integer no bigger than D minus 1. I want to show R is 0, so that D divides K. But then A, so what is A to the K? This is A to the DQ plus R. This is A to the DQ times A to the R. A to the DQ is A to the D to the Q. But A is order D. Oh, and this is the identity. A to the K is the identity. But A to the D is also the identity. So that's E to the Q times A to the R, and multiplying the identity by itself is just the identity. We get A to the R equals E. And R is between 0 and D minus 1. So R is strictly smaller than D. But there's no positive integer R less than D that satisfies this equation. That's the definition of the order D of the element A. So R cannot be positive. So R has to be 0. And if R is 0, K is DQ, D divides K. That's what we wanted to prove. So if an element in a group has finite order, D, then an integer K satisfies A to the K equals the identity, if and only if that number K is divisible by D. And we can now prove one of the major theorems in algebra, which is called Lagrange's theorem. Lagrange's theorem, and you'll see in a moment, this is a generalization of the Fermat theorem and the Euler theorem we used when we were working with RSA. So the G be a finite group, and let A be an element of the group G. The order of A divides the order of the group. Remember, the order of the group is the number of elements in the group. And another way of saying is that if we let N be the order of G, and we let D be the order of the element A in the group G, then D divides A. Then D divides N. And D divides N, and A to the N is equal to the identity. Because this is really one of the basic facts in all of mathematics. Let's see. So the authors are a little bit lazy, and they only give the proof in the case when the group G is commutative or abelian. So suppose we let G have order n. So G consists of n elements, G1, G2, G3, up to G sub n. These are the n distinct elements in the group G. And let, I'll call this set S of A, for the what you get by multiplying every element in the group on the left by A. AG1, AG2, AG3, up to AGN. So I claim, first of all, that the cardinality of SA is equal to n. That is, the n elements in this set are distinct. And the proof is very simple. If AGI equals AGJ, then you can multiply on the left by A inverse. A inverse AGI will be A inverse AGJ. But A inverse A is the identity. The identity times GI is just GI. Similarly, A inverse A is the identity. This is just GJ. So AGI equals AGJ, just multiplying on the left by the inverse of A says GI equals GJ. So these elements are distinct. So if I but there are only elements in the group. There are only n elements in the group. So the set G has to be equal to the set SA. So if I multiply together all the elements in SA, AG1, AG2, AG3, up to AGN, this is just the elements of the group in some order. If the group's abelian, the order you multiply in doesn't matter. This is just going to be G1, G2, G3, up to Gn. And again, rearranging all this, I have A n times A to the power n, G1, G2, up to Gn, equals this. So I have A to the n times the product of the elements of the group equals the product of the elements in the group. If I multiply by the inverse of this, I just cancel this. I get a to the n equals the identity. So if the cardinality of G is n, and G is abelian, then a to the n equals the identity for all a in the group. And so if a has order d, if we just proved if a has order d and a to some number is the identity, then d divides n. What was an example that we've already seen? Suppose we let G be Z mod PZ star, or in FP star. This is the non-zero congruence classes mod P, 1, 2, 3, up to P minus 1. So this is a multiplicative group. And in this group, the order of this group is P minus 1. So if A is in the group, then the greatest common divisor of A and P is 1. And A to the order of the group P minus 1 is going to be congruent to 1 mod P. This is Fermat's theorem. But we see Fermat's theorem is just a special case of Lagrange's theorem. The proof in the non-abelian case isn't hard at all, but you're really only going to be dealing with abelian groups. Okay. Now, we're going to be able, in a very interesting way, and not at all obvious, to associate an abelian group to every elliptic curve. So let's see. So for us, an elliptic curve is always going to have, it's going to be, this is our definition, it's going to be a curve of the form y squared equals x cubed plus ax plus b. So a quadratic y squared equals a cubic, and the cubic, for us, we're only going to consider cubics which are monic, that is, the coefficient of x cubed is 1, and there's no quadratic term. So it's just x cubed plus ax plus b. There's no x squared term. So for example, if we take the elliptic curve E1 to be y squared equals x cubed minus 3x plus 3, it's hard to graph these by hand. The computer can graph it. But this is a curve. It looks like that. If we take the elliptic curve y squared equals x cubed minus 6x plus 5, that's an elliptic curve which looks like that and this. So there's like a sort of a finite piece and an infinite piece for this elliptic curve. This, and I'm going to define a way to add 2 points on this elliptic curve in a manner that gives us a group. Without our group operation, there'll be a way to say if you have 1 point on a curve and another point on the curve, you can add these two. If maybe this is A and this is B. And here on the curve will be the point A plus B. There'd be a way to add 2 points in the curve and get a third point on the curve. And it will be shown. It's hard. I don't know how much of it we'll do because it's a lot of algebraic manipulation. That this operation is associative, there's an identity, and every element has an inverse. And it's abelian, this community. So there will be associated to this elliptic curve will be a group. And what we're going to learn next week is how to construct a cryptographic system based on addition of points on this elliptic curve. If you think about RSA, RSA is based on choosing a number n. You have z mod nz star, looking at numbers relatively prime to n. And so this is an abelian group, and somehow using this finite abelian group, we got a RSA out of it. It's a little bit clever, but that's what really that was the algebra involved. And next week we'll see how, by defining addition of points on this elliptic curve, we also can construct a crypto system. And that, I guess, is really enough for today. So that we pause at this point. A question from the review sheet?
Yes, Professor. I had just 2 more, and then I think I should be fine. I'm trying to look. The first one, I remember one of them, but I'm gonna look for the other one. But the first one I wanted to ask about was it was number 7, like with proving that GCD by computing and stuff like that.
Well, okay, so that's just the Euclidean algorithm,
Oh, that's just the Euclidean algorithm.
right? That is, you take 31,
Mhm.
divide it by 7, you get a remainder of 3. Take 7, divide it by 3, you get a remainder of 1. Take 3, divide it by 1, and you get a remainder of 0. So the greatest common divisor is 1. And then you work backwards. 1 is 7 minus 3 times 2. That's 7 minus 3 times 2, but 3 you can write as 31 minus 7 times 4. So what is this? You have 7 plus 8 times 7. So you have 7 times 9 minus 31 times 2. So this is 1 is 7 times 9 plus 31 times minus 2. So this is your number x, and this is your number y. And you just check, this just says 63 minus 62 is 1. So this is correct. So 1 is 7x plus 31y. X is 9, y is minus 2.
Okay.
Professor, can I ask you, can you do number 3, please?
Which one?
Number 3?
Number 3. Well, yeah. So the powers of 2, 1, 2, 4, 8, 16, and so forth. 13, the largest power you can pick is 8, the next is 4, the next is 1. So this is 2 to the 0 plus 2 squared plus 2 cubed. So that's 13 as a sum of, sorry, did you say 3 or 4?
3, Professor, you're doing number 4, I think.
Okay. And you want number 3?
Yes, please.
Okay. So for number 3, you have to factor 3960. So that's like 396 times 10. 396 is 3 times 132. 10 is 2 times 5. Just keep factoring. 3 at 132, this is 4 times 34, I think. No, 4 times 33 times 2 times 5. So I have, this is 3 times 2 times 2 times 3 times 11 times 2 times 5. You put this together, I mean, you're just doing, elementary school arithmetic. This is 2 cubed, if I have it correct, 3 squared, 5 to the first power, 11 to the first power. So that's the prime factorization of 3960. So V3 of 3960, that's the highest power of 3 that goes into this number, which looks like it's the second power. V5 of 3960, highest power of 5 that goes into this number is the first power. V7 of 3960, that's the highest power of 7 that goes into this. 7 isn't here, or if you like, it's like 7 to the 0, which is 1. That's the 0th power. The 11 of 3960 is 1.
So is this factoring the primes, Professor, for this one?
Well, it's asking you, when you write the number as a product of prime numbers, what is the power of the prime? The VP of the number is the highest power of the prime P that divides the number. That's the definition.
Okay.
Thank you, Professor.
Okay. All right. Good luck this afternoon.
And Professor, quick question. It's not about the review, but like, I know we have like 2 hours for the exam, right? Like, do you know how long it will take? Because like, what if like we use up all the time and then, scanning stuff like that and we don't turn it in within like that time frame? Is there like leeway or anything like
Well,
that?
if it's a couple minutes late because of scanning, it's fine. But one of the instructions will be, if you're turning in late, explain why.
Oh, like what's it like when you upload submission, you just explain like on the comment or something like that, right?
Yeah, that's right. I mean, if it's a couple of minutes late, it doesn't matter. But, if you turn it in an hour late, I want to know why.
And Professor, what's it? So based on like how you made the exam, do you think we'll like take up all the time, or do you think it'll be like more like an hour and a half type thing to
Depends on the student.
Okay.
Right? I mean, whatever it takes, it takes.
Okay.
Up to 2 hours.
Right. Thank you,
So-
Professor.
So,
Okay.
Professor, it will be in Blackboard, right?
Yes.
Okay, thank you. Have a good day, Professor.
Okay, bye.
Bye, Professor. Thank you.